Welcome to the Explainer. Today, we're going to completely demystify the mechanics of inverse trigonometric functions. We're going to take this all the way from the absolute foundational rules right up to solving complex summation series. If you've ever stared at a page of inverse trig equations and felt like, you were trying to read some ancient, undecipherable language, well, you're in exactly the right place. We're going to decode these notes step by step, zeroing in on the logical flow that makes this specific branch of math so incredibly elegant. Okay, so let's jump right into the fundamental problem here. Think about it. How do you reverse a function that literally repeats forever? You already know the core paradox of trig waves. They just keep going. Because they're many to one, they completely fail the horizontal line test. That means true mathematical inversion is, well, it's impossible without some sort of deliberate intervention. You simply can't reverse a function if you have absolutely no idea which of those infinite starting points you originally came from, right? So here's our roadmap for today. We're hitting 1, the bijectivity problem, 2, principal values and quadrants, 3, visualizing inverse properties, 4, conversions and core formulas, and finally 5, solving summation series.
All right, part 1, the bijectivity problem.
To actually have an inverse, we have to establish a one-to-one mapping. Notice how the notes map out the solution to our endless wave problem. Look at those red dotted lines physically restricting the domain of the sine wave. By essentially chopping off the infinite tails and only looking at the chunk of the wave between negative pi over 2 and positive pi over 2, we isolate a single non-repeating curve. The notes refer to this numerically least ordered pair as the principal value or principal range. By forcing this domain restriction, we make the function bijective, giving us one unique output for every single input. Problem solved. Moving right along to part 2, principal values and quadrants. Now that we've isolated a workable piece of the function, we really need to understand the rules of where these inverse values live on a standard coordinate plane. Look at how they're categorized based on the input sign. For any positive value of x, every single inverse trig function outputs into the first quadrant. Super clean, super unified. But if x is negative, the function's split into two distinct camps. Sine inverse, tangent inverse, and cosecant inverse, they output to the fourth quadrant. Meanwhile, cosine inverse, secant inverse, and cotangent inverse shift over to the second quadrant. The absolutely crucial takeaway here, the third quadrant is completely abandoned, literally never used. If we let values slip into that third quadrant, we'd risk making the whole thing many to one again, totally breaking the boundaries we just built. Okay, part 3, visualizing inverse properties. It is so easy to get completely lost in the algebra when you start seeing expressions like sine inverse of sine of x. But actually, graphing out these periodic properties reveals exactly what the math is doing behind the scenes. And this perfectly illustrates the contrast between the functions. On the left, check out the graph for sine inverse of sine of x. It's this periodic zigzag that slices straight through the origin, bouncing up and down with a period of 2 pi. But then, look at the graph for cosine inverse of cosine of x on the right. Because its principal value restricts it to between 0 and pi, the entire zigzag pattern bounces strictly above the x-axis. It never dips below 0. Seeing it laid out visually like this just makes those abstract domain constraints instantly click, doesn't it? Which brings us to part 4, conversions and core formulas. With our visual understanding locked in, we can start converting between different inverse functions. And look, you might see a massive page of inverse trig identities and panic, thinking you have to rote memorize every single one. You don't. Actually, scratch that, you really shouldn't. You just need to follow a few simple logical steps to build a right triangle. Just set an angle, let's call it theta, equal to your initial inverse function. Map the given variable to the sides of a triangle, use good old Pythagoras to find the missing side, and boom, you can just read any other inverse function right off the geometry. Let's see this in action. This diagram shows the triangle method transforming a cosine inverse into a sine inverse. If theta equals the cosine inverse of x, then the cosine of theta is just x over 1. So on our right triangle, the adjacent side is x and the hypotenuse is 1. Run the Pythagorean theorem, and the opposite side becomes the square root of 1 minus x squared. Now, you want the sine inverse? Easy. Sine is opposite over hypotenuse, which gives us the square root of 1 minus x squared. See? The geometry does all the heavy lifting for you. Now, fair warning, once we start adding these inverse functions together, the formulas do get noticeably more complex. And that's because context is everything here. The actual values of your variables entirely dictate which version of the formula you have to use. Take a look at these formulas for adding two tangent inverses. Notice how the single formula fractures into totally different cases. If the product of x and y is less than 1, you just use the straightforward addition formula. Simple. But if x and y are positive and their product is greater than 1, well, the sum of their angles would actually exceed pi over 2, pushing the result completely out of the allowed principal range. So to fix it, the formula forces you to add a pi term to adjust the angle back into the correct domain. It's a built-in safety valve, proving exactly why our initial domain restrictions are absolutely crucial.
Finally, Part 5, Solving Summation Series, the grand finale.
We are going to apply everything we've just learned, the domains, the triangles, the formulas, to conquer summation series. When you face a seemingly endless series of inverse trig functions to add together, brute force is not going to cut it. The strategy here is essentially to set up a massive, cascading chain reaction of mathematical cancellations. You identify the general nth term, maneuver it algebraically into a tangent inverse format, and then hit it with our formulas in reverse to split it apart. Let's look closely at this specific maneuver. The author takes a really complex, single term and deliberately forces it into the format of the tangent inverse subtraction formula. By expertly converting this one term into a difference of two consecutive tangent inverses, specifically tangent inverse of n plus 1 minus tangent inverse of n, we perfectly prime the series for telescoping. We're literally turning a giant wall of addition into a sequence of interlocking positive and negative parts. And here is the payoff. When you write out the expanded series vertically, watch how the middle terms just beautifully destroy each other in red ink. A positive tangent inverse of 2 is wiped out by a negative tangent inverse of 2. Positive 3 wipes out negative 3. This cascading cancellation slices right through the heart of the series, leaving only the very first term and the very last term standing. Think about that. A terrifying infinite series collapses down to just pi over 2 minus tangent inverse of 2. It is, frankly, a masterpiece of algebraic structuring. So, thank you for joining me on this explainer. I hope you'll keep looking for the underlying structure beneath all these intimidating formulas. I want to leave you with a thought. The next time you see a robotic arm moving with absolutely perfect precision, ask yourself, how do these very same principal value restrictions, the ones we just learned, prevent that machine from spinning entirely out of control?